Hello, I'm Sean Bowe. I work as an engineer for the Zcash company, not the foundation. The company is a for-profit that launched the Zcash network about a year and a half ago. So Zcash implements the Zero Cash protocol, which is a protocol for private payments using zero-knowledge proofs. So a year and a half ago we launched it, but actually it's been around for a lot longer. It started with Zero Coin many years ago, and then when ZK became practical, Zero Cash came about, and then an academic prototype showed up at some point, and then we actually spent some time to deploy it in practice and secure it and fix some bugs and stuff like that. So now we have a system running. There's $1 billion riding on a lot of papers that were authored by people in this room, so hopefully everything's okay. So Zero Cash, just to kind of give a quick recap of how Zero Cash works. Basically, and this is kind of the terminology that we use, not really the Zero Cash paper, but there are these things called notes. You can think of them kind of like UTXOs in Bitcoin. They contain a value and a key that's allowed to spend the value, public key. And when you're sending people money, you create a note, you commit to it, you make a commitment, and you place it in an accumulator, which in our case is a Merkle tree. So all the nodes on the network have a Merkle tree, and then they just throw these note commitments into the tree. And when you're trying to spend some money, then you reveal this nullifier that's kind of like a signature of the spend or a serial number. It doesn't indicate which note is being spent, even to the person who created it, but it does. It's deterministic, and it's used to prevent double spending, because you can just prevent transactions that reveal it twice. So, in order to make this work, we use ZK snarks. So we prove that we know a path in the tree. We prove that that is to a commitment. We can open the commitment. We know the private key, which in Zero Cash is just the SHA-256 of some other key. We prove that we computed the nullifier correctly, which in our case was SHA-256 with the seed, modeled as a PRF with the seed as being the secret key, and then we prove that the transaction value is all balanced up. So ZK snarks let us do all this, but they have a reputation for being really slow, because unfortunately that's mostly our fault. They're not that slow, they're actually pretty fast, but we used SHA-256 a lot for pretty much everything in Zero Cash. We used it for the tree, we used it for a bunch of things where we only needed collision resistance and didn't need all these other properties, or where there were other options where we could even use those instead. So we're making a network upgrade to Zcash finally, coming about sometime in September, and it's going to basically, the focus is to make Zcash much faster, and so in order to improve that, we have to decrease the circuit size and move away from these SHA-256 based primitives. We also wanted to add a few features that I won't go into in too much detail right now. So the effect of the performance improvements is pretty substantial. So we get 40-second proofs down to about 2 seconds, and that's worst case. Depending on what you're doing, it can be faster, and we get verification down to about 5 milliseconds. It might be closer to like 6 or 7 or something like that. I don't know, but it's pretty good. So to get us on this way, we have to make some modifications. So the first thing is to abandon this curve BN128. We're going to completely rid ourselves of this curve in the next upgrade. So it does have closer to 100 bits of security under really conservative